I'm back and I'm getting ready to aggravate you about halogens all over again. Isn't that sweet of me? Yes, I know, I know. You love me. I'm your favorite instructor ever. And that's because I aggravate you all the time with these reactions. I know that. I know. You don't have to tell me. All right, so what you're seeing on the screen is a review. If you didn't learn this in the last video, you better go back and watch it. And this review is talking about the mechanism of bromine or chlorine addition to an alkene. And we said that a cyclic bromonium or a cyclic chloronium ion happens in this reaction. Well, how do we know that? Okay, well, what's our other option? That will allow us to determine that a little bit better. So in the real mechanism, what actually happens is that Br2 or Cl2 down, fly in. They get near the double bond. This double bond is negative. One of these bromines can become slightly positive, and then that will force the twin, the other bromine, out. Bing! Off. Away you go. Don't need you anymore. Leave me alone. That's what that bromine says to the other one. Okay, well, when this happens, this bromine that made the decision to hit the curb, it's going to leave behind this other bromine that is going to end up being slightly positive. All right? And that bromine has a very hard time making up on which carbon he likes the best. Sometimes it's the left, sometimes it's the right. Sometimes it's the left, sometimes it's the right. And it holds on to both of these. And we call this the cyclic bromonium or the cyclic chloronium ion. And it will hold on to both of those carbons at the same time until the other twin decides to come back and save that brother or that sister and say, I'm here. Remember, I said I'm posting the bail money to get you out of jail. So that bromine comes in, and the first bromine acts as an electrophile. Because it is an electrophile, look at it, it's positive. And like the other electrophiles, we've only seen hydrogen behave that way up to this point. The other electrophiles add to the carbon with the most amount of hydrogens. I mean, that's what they did. Every time that we've introduced one of these reactions, that is the very first step so far, wasn't it? We added HBr, H added to the other H's. We added HOH, H added to the carbon with the most H's. We added H with an alcohol, the H added to the carbon with the most H's. Folks, it doesn't change here either. There's no difference. The electrophile just happens to be bromine here, not hydrogen. So that first bromine, which is that electrophile, is going to add on to the carbons with the most amount of H's. The difference is that we just haven't seen this before. And that's all right. Not a big deal. It's still the same procedure. We're just using something different with this. That's all. That's all we're doing. So this bromine makes the decision, hey, there's no difference in these two carbons the way they're drawn. It doesn't really matter which one I go to. I'm going to cleave the bond over here to the left-hand side, though, because that's how the arrows are drawn. And then this second bromine will come in at the same time and attach to that carbon that this first bromine is getting ready to leave. And we said that this is one of the reasons that we do not see rearrangement take place in the halogen additions. This is why this happens. All right, well, the other route that could go on here would be, all right, well, what were the other steps of the reactions before? This is what it was. Why does the cyclic have to form? Well, let's say that it doesn't. Bromine comes in, bromine looks at this double bond, bromine breaks the double bond to a single, two sides of attachment open up, and bromine goes on to one, and then a carbocation is formed on the other. Now let's talk about that setup for a minute. Bromine is very electronegative. Bromine is very electron greedy. There's 3 sets of electrons around that bromine. You see that. I can see that. Because of that, this makes bromine a very negative area. And look at right beside of it. Right beside of it is a carbocation that has formed. Oh, no. No. This is not good for the organic. Look, I've got 2 carbons. They're side by side. One's positive, one's negative. You know good and well something is going to happen between them. I mean, someone single in one house, someone single in the neighboring house, and they are living side by side and they're attracted to each other, you can imagine what's going to happen. So that carbocation and that negative bromine makes that particular setup very unstable compared to something that looks like this, where bromine is trying to figure out what he wants to do in the beginning until the other bromine can actually come in and stabilize that whole system. And in one fell concerted swoop, one bond pops and the other bond forms. And we get two bromines onto the molecule. The reason that the top route does not happen is simply due to the fact that they are neighboring carbons, and bromine is huge as far as size goes. And that bromine, because it is fairly large, takes up a lot of space, and that bromine, because it carries all of those free pairs of electrons, is going to be negative, and that bromine, with the massive amount of space that it takes up, is invading on the carbocation area, and this starts to interfere and reduces the stability of this transitional period of the molecule where this will not form. That is not an ideal setup for it, and it will never happen, and that is why this happens in a cyclic form instead. So in the last video, we talked about molecules reacting with chlorine in methylene chloride. That's another way to write methylene chloride, right? I could do DCM. That's not a problem. I could do MECl2 also. Well, here they just wrote out the chemical structure. We drew that actually in the last video, and here they're just going to write it out, CH2Cl2. It all means the same thing. So this is just the solvent, right? This is the solvent. It doesn't participate in the reaction. The double bond breaks. Cl goes onto one spot. Cl goes onto the other spot. And that's how these reactions happen. Here's another one, and this uses bromine. So here the double bond breaks, and we still use methylene chloride as the solvent, and bromine goes on one, and bromine goes on the other. And again, we also said this rearrangement does not occur. It can't occur because that bromine is attached to those two carbons at one time in a cyclic ion, and those are the locations that the bromine or the chlorine will go on. It's just, that's the way it is, all right? No rearrangement is going to take place. In addition to that, we also spitted out a term, and that term is vicinal. And anytime we see vicinal come through, that means side by side. So here's a carbon that has a bromine, and right beside of it is a carbon that also has a bromine. So we call that a vicinal dibromide. So this is not the only type of halogen reaction that alkenes can undergo, as you can imagine. Okay, there's going to be another route, another option that we might see in organic that's going to be pretty common. And this is an alkene, just like before. This is where we're always starting. And I'm still going to react it with something like Br2 or Cl2. That's not a big deal. But this time I'm not going to use methylene chloride. Now, I know what you're saying. You're going to say, well, I thought you told me that this had to be a solvent to keep it in solution. Yeah, it does. But we can use another solvent. We can use something else that will help keep the bromine and chlorine in solution. It might not be the best solvent, but it would be a solvent that would at least allow the interaction to take place there in the very beginning. And one of those other solvents is water. Okay, I know what you're going to tell me. You told me that water's polar and it's not going to react with alkenes. I did, didn't I? But you know what? We used water already in a reaction. We just made sure that it was water and a little bit of acid. And then once we did that, this reaction happened. And we took this alkene, which was a double bond that was very organic-y, and we put alcohol groups on it. And we increased the polarity on it. And all of a sudden, we got a product that was nothing like the reagent. That was okay. And this is going to be okay too. Now, I don't need acid here. And the question's why? Why don't I need acid in this case, but I needed acid in the first case? I mean, don't we need acid to get water to be active? Well, we did. It was a jump start. It was a jump start in the reaction, and the acid was there to help the protonation, which allowed this electrophile to happen first. But folks, we don't need that here. And the reason is because bromine's going to do what bromine did in the other example. Bromine's going to come into the alkene, and bromine is going to look at this double bond, and it's going to say, you know what, you need a break. And I'm going to grab both of you at one time, and we see a breakage of the double bond, and then we also see this kind of positive bromine form in the cyclic bromonium or chloronium ion that we saw before. The first step of this reaction is no different. It's no different. So over here, I'm just going to draw two more legs to tell you it could be other things that needed to be there if they wanted to be there, not a problem. So bromine is going to hold on to both, but this time when bromine spit off a Br minus, folks, we also have water that's involved in this process now as well. And this is also a negative area, isn't it? It is. It's a negative area. In addition to that, this is regarded as the solvent. So as far as the amount goes, there is a larger concentration amount of water hanging around in this flask than there is of the bromine. Otherwise, the bromine would be the solvent and the water would be the solute. You use those terms in general chemistry. So now we have to actively think. We have to say, okay, listen, there is a chance that bromine that was kicked off will come around and attack this other carbon, and things will go as planned like normal as in a methylene chloride reaction. There's product number one. But it's not the major product. And the reason it's not the major product is because we have things like water that is in there in a tremendously high amount because it's a solvent. And statistically, water has a better chance of coming into this and attacking that carbon and beating it out, beating that bromine out before that second bromine has a chance to come in and do its job. Okay, well, this bromine that's a minus, it might not stay around as a minus. If it can't come in and react with this other carbon in this cyclic structure, what happens to this bromine? Well, this water's in a large amount, isn't it? This bromine's negative, isn't it? Those hydrogens are positive, aren't they? And watch this. This bromine could actually come to the water molecule and say, oh, you're polar. Unlike methylene chloride. Methylene chloride was nonpolar, equal sharing. But in this case, bromine could look at the water molecule and say, you're polar. Hey, hydrogen, you want to come my way? And hydrogen's going to do, what do you think? Okay. And pop it goes. And this will form HBr, acidic conditions. Well, these electrons will be shifted toward that oxygen. This gives us an OH at this point, and that negative area of the OH will come on and attach to one of these carbons. That way the bromine can take those electrons and clear up himself to become neutral. This OH is going to go onto that carbon and sit down to make an alcohol, and then we have HBr that gets generated as a byproduct as well. All right, so our initial or our final product here is going to be bromine added through the use of Makovnikov and also OH. And that is the addition of Br2 and water. Br or Cl will go on first, and it plays with other hydrogens following Makovnikov rule. And then OH from the water will go on to the other carbon. Okay, we have a special term for this. This is called a halo for halogen and hydron for water. So this product we do have a term that's associated with it to describe it, and we call it a halohydrin. Now, they're really not alcohols. I know that they have OH groups, and OHs are regarded as an alcohol functional group, and that's fine. But, you know, the difference here is that right beside of that, we also have a halogen. So this makes it a special type of molecule. We don't see this very often. And whenever we see these kind of weird little things that go on, we like to give them special names because they're special molecules. We want them to feel special. So halohydrin is what we call that particular type of functional group. Makovnikov's rule still follows. There is no difference in it. The only thing that I'll say is that the Br or the Cl will act as the hydrogen in the very first step. All right, so let me give you some real examples. Okay, let's do some real ones with real molecules so you can see how these things are going to work. So I'm going to take CH3, and then we'll do CH, double bond, CH2, and then I'll bring in Br2, and on top of this arrow, we'll do water. Sometimes they'll write it below the arrow. Doesn't make a difference, right? I know that seems kind of silly for me to say, but some people do get confused with that. They think it means something different, and it doesn't. All right, so I'm going to, just like before, redraw what I start with. CH3, CH, double bond, CH2. I'm going to break the double bond. Two sites of attachment open up. There we go. The Br from the bromine will come in first. That follows Makovnikov's rule. Treat it like hydrogen. Out of these two carbons, the carbon to the left has 1, the carbon to the right has 2, so therefore my bromine will go on that location. Makovnikov's rule follows first. That allows this to form a carbocation. That's a secondary carbocation, which is going to be more stable than the other route, which would have been primary. And then the OH from the water molecule will come in and go there. That is a halohydrin. In particular, it's a bromohydrin, and that is the major product for this reaction. Okay, but I do want you to understand that another route could exist, and we do get it. That double bond could break. Two sites of attachment open up here and here. The first round, that bromine will add on to the carbon with the most amount of hydrogen. And then it could, because that did spit off bromine minus, that bromine minus could beat out the OH. It just really depends on the location and how fast it can swoop in and take that spot. But this would be the minor product. And the reason that this is major, again, is because water is in a higher concentration because it's a solvent. Bromine is there as well, though. Bromine, that Br minus, can come in and it can attach to that molecule. That's not a problem for it. It can happen. And we get something very similar to something like a Br2 and a DCM reaction would give us. That's what that would be. But because water is in higher concentration, because there's more of it, statistically speaking, it could beat out the bromine in more cases. And that is why this is the major product for that reaction. Can we name this? Yeah, we can name this. This is not a problem. Up here at the top, we can name that as well. If I name the reagent, this is a prop, and it's a propene. And it's a 1-propene because the double bond happens at the first carbon. Propene reacts with bromine in the presence of water. And what we would end up getting is a propane. There's my longest carbon chain, right? If I look at the OH group, that makes this an alcohol. So not propane, but propanol. And if I look from the left, that's a 2. If I look from the right, it's a 2. So that's a tie. It's going to be a 2-propanol no matter what we do. And then we look at the other groups that are around that to make a decision on how to number it. And bromine is closest to the right-hand side. So this is going to be carbon 1, this is going to be carbon 2, and this is going to be carbon 3. So on carbon 1, we've got a bromo, And then on carbon 2, that is where our alcohol group is going to be. So propene reacts with bromine in the presence of water to give us 1-bromo-2-propanol. All right, so there's your example of how to handle these halogens that have water associated with the compound or the reaction. Okay, so let's do another one. Let's do CH3, CH, double bond, carbon, CH3 on top, CH3 on the bottom. And we add chlorine in as well as water. What do we get? You tell me. You're pros at this now. I know you are. So you tell me what's going to happen. Pause this video, write down what you think is going to form as a product, and then replay the video or hit play button. Maybe don't replay me. I don't even think I could watch me again. And then double check your answer against mine. See if you're right. I guarantee you will be. All right. So just like before, I'm going to rewrite the starting reagent. And here we are. And I know that this double bond's going to break. Bink. My whole screen moved. Look at that. I'm getting really excited now. All right. So double bond's going to break. Two sides of attachment open up there and there. The chlorine gets added on first. That's what starts the reaction in the first place. We regard that as the electrophile. So that chlorine plays with other hydrogens. To the left, I have one. To the right, I don't have any. So chlorine goes there. Well, I could get another chlorine to get added on. That's a minor product, though, and that chlorine would have added on right there. So this is the minor product that could form from a reaction, but it's not the major one. And the reason it's not the major one is OH is the solvent. We have tons of water compared to that chlorine. So that water is going to give me the OH group, and that is the negative piece that gets added on to that carbocation. So folks, there you go. There's the product for the reaction of the alkene with chlorine in water to give me a product. Now let's name them. I told you, I love examples. I love to reaffirm that you know what you're doing in this class. So let's name the first reagent up here at the very top. Longest carbon chain, 1, 2, 3, 4, butene. And there you go. All right, if I look at that double bond, 1, 2 from the left, 1, 2 from the right, it's going to be a 2 no matter which way we go. But you look at the other substituents now in order to determine how you're going to number. CH3 is closest to the right-hand side. So I number closest to the right-hand side. 1, 2, 3, 4. And at carbon number 2, I have a methyl group. So 2-methyl-2-butene reacts with chlorine in the presence of water to give us, and we can name that as well. That's not a big deal for me. I named the longest carbon chain. The longest carbon chain can go straight across here. That's going to be the easiest. 1, 2, 3, 4, butane. Well, I look at the OH group. That makes it an alcohol. I number closest to its side. 1, 2, 3 from the left or 1, 2 from the right. I'm going to go 1, 2, 3, 4. It gives me the lowest number. On carbon number 2, I have an alcohol group. So that means I erase the E and I add OL. 2-butanol. Well, on carbon number 2, I also have a methyl group. And on carbon number 3, I have a chloro group. Which comes first, chloro or methyl? I hope you tell me chloro, because if so, you know your alphabet. So 3-chloro, and then 2-methyl, 2-butanol. Look at that, folks. That's organic beauty right there. 2-methyl-2-butene reacts with chlorine in the presence of water to give us 3-chloro-2-methyl-2-butanol. I've taken an alkene in the very beginning that I could have gotten from crude oil. Who knows where it came from, but that could be a possibility. I chlorinate and bubble chlorine gas through it, and I have generated this alcohol compound that we didn't have before. And that alcohol compound has a little bit of polarity that's associated with it. It also has a chlorinated group on it as well that's going to be very important later on down the road and organic. But this gives me a completely different organic structure with completely different properties that we might need in a laboratory environment. And that is how we make these typical products. All right. So there's the story with halohydrins. Now, if you really want to know the full mechanism detail, I kind of did it all in one step for you, but here's just another view of it. The bromine or the chlorine comes in first. You get the cyclic molecule that begins to happen just like before. We do have water, and here's where it kind of changes from when I did it. I just kind of did it all in one fell swoop, but they're going to separate these out in different stages for you. So when this bromine goes on to form the cyclic ion, the water molecule as a whole will go on to this carbon, and you'll see OHH that gets attached. This is when the oxygen knows that it really does have a problem at this point, and this water molecule can go in and attack that hydrogen and rip it off and give you OH here. And then it can regenerate acid. All right, but the bromine can also do it as well. And you got to keep in mind, water is, of course, the solvent, so there's more chances of water of doing it. So that is a possibility of it ripping the hydrogen off and generating the acid. And bromine can also do it as well. Bromine can go in and rip the H off because it's negative, just like that water is. And that forms an acid, HBr, and that's what kind of is represented there as well. H3O+, that's also an acid. So either way will work, not a big deal. But this is how the reaction goes forward. So this is where the video is going to stop. And we're not done with halogens yet. We are going to go through and we are going to attempt these reactions with something else now if water was not present. So we've done an example with methylene chloride, which is organic-y, nonpolar. We've done examples with water, which is really totally different, H2O, polar. And we've been dabbling a little bit with alcohols, haven't we? So what if we had an alcohol there? What changes? Anything? What kind of products get formed? These we'll talk about in the next video.